It's my pleasure to present Adriano da Silva from Unicamp. He works on geometric control theory. He'll talk about structural properties on the bounded control set of linear control system. So, Adriano? Let me give a time to make the arrangements.
Excuse me,
sorry for that.
Let me help him. I think you are sharing your screen using another page.
Just 1 second. I can substitute the presentation of Philip. Can I do that?
Yeah, you can.
I cannot suppress my presentation. I have a problem.
Just 1 second.
In the other up screen, okay. Up your screen, you are sharing your screen using another.
Yes.
Is that okay?
Okay.
Okay. Can I start?
Sure.
Sorry,
nice to have you here, Adriano.
Okay. So it's a pleasure being here. It's strange to thank the organizers. I'm here, but as Lucas and anyone said, the people from the Fora, they are the head of the spear. So thanks to them, thanks to us, but thanks in special to them. And thank also for the opportunity to talk to a very distinctive crowd. My colleagues, so very different areas, is always really nice to do. So what I will be talking today, it's basically a compiled of some results that I obtained during the last years, mainly with Professor Ayala, but also with other collaborators concerning linear control systems. Yes, the idea here is finish with the last properties that we got concerning bounded ones, but I will talk a little bit about also the geometric relationship that has a natural derivation that you have associated to a linear vector field. What does that how does that behaves with relationship to your actual control system? Okay, so as I said, basically what I'll do first is just to define a linear system, then comment on these properties. And Professor Joan already said what's a linear vector field. But a linear control system here for us will be a family of differential equations, ordinary differential equations, on a connected Lie group. And the Lie algebra here, we choose invariant, identified with the invariant vector fields, the right or left invariant vector fields with one fixed. And the one that we choose also the vector field here in this expression. Okay, so it's basically this family of ordinary differential equations. And what you have here is that your function u here that has coordinates u1 up to un, they are basically measurable, and they have image inside a compact convex subset of your Euclidean space, m-dimensional Euclidean space, and it contains 0 in the interior. So this is not a very restrictive condition. You can also choose, you can basically, for most of the problems, the problem of controllability and so on, you can choose piecewise constant functions. There is no problem, because you can approximate this kind of, the solution of this system. So we choose this one because, as showed by Professor Colones and Clement in their book, you have a nice property of continuity on the control part of the solution of your system sigma g. Okay, so, and as I said, your vector fields Yj here, they are invariant ones, and they are choosing, agreeing with your with the choice that you made for the algebra here. So if you choose right invariant, your vectors are also right invariant ones, and your vector field X is a linear vector field, and as Professor Joan said, being linear, one of the equivalents of the definition of a linear vector field is that it is a complete vector field, and its associated flow is just a one parameter subgroup of the group of the automorphism of G. Okay, and I will define just some more structure that you need here in order to talk about controllability and also controllable control sets. You need to define what's the attainable set of your system from a given point. It's basically the points that you can reach starting from G in this case. Okay, so basically, if you think about, if you think that your system there is just the constants that I said they're just piecewise ones, and then what you get, basically, this set is just concatenation of solution of some fixed vector field. Okay, if you look at the expression here and you ask this ui up to um to be constant, you have a vector field here fixed, and then you can think of this of its solution, and then basically here what you're seeing is basically the closure of concatenation of this parts of this points starting from G. And a control set here in this context is basically a subset that's non-empty, and it has two main properties, and it's maximal with this kind of property. So basically you ask for a weak invariance is the first condition. A weak invariance in here just means that you can remain inside your control set, or the subset that you call control set, by at least one control. There is one control that you remains inside for positive time, and the second one is that your set D, all the points are approximated controllable, in the sense that you can, for any two given points in your control set, you can epsilon approximated both of these points by a solution of your system, by this kind of thing here. This phi here just denotes the solution of your system sigma G. Okay, so this kind of concept, the control set, they generalize the concept of controllability, of full controllability, in the sense that you can in fact join 2 points. Okay, there's approximated controllability here. It's a space of generalization, and it actually happens inside the interior of your control set. If you have a control set with no empty interior, you have in fact controllability inside this control set, in the sense that you can join 2 points by a positive threshold. Okay, so, and the great advantage of working with the LCS, the linear control system, is that you can in fact associate a linear map, and that makes things a little bit easier. And you can approximate a linear map that, in the general case of an arbitrary algebra, it's a derivation of the algebra, and it's connected with, not in fact with the linear control system, but with the drift of the linear control system, meaning the linear vector field. And this association, the relationship between the derivation that you obtain and the flow of your linear vector field is given by this relationship here. Okay, and this relationship allows us to define what we call dynamical subgroups. That's basically subgroups of your group G that are related with the generalized eigenspace of this map A here. Okay, so G plus here, the Lie algebra G plus is just the sum of the generalized eigenspace that is associated with eigenvalues with positive real part of the matrix A, and here positive negative real parts, and here 0 real parts. Okay, so basically what you have here is that both of this subgroup, they are G plus and G minus, they are nilpotent one because the algebra associated are nilpotent, and G0 can be lots of things. Okay, it can be general and can be any kind of group. And what happens is that this kind of result, it was already known in the Euclidean case. This is a very well-known linear control system on Rn. Okay, and when we look at this here, basically the matrix A is it's being replaced by the linear vector field, and this B here, you can see this U. Remember that U is a function with m coordinates, so you can look just at the product of each of this function by the columns of B, and then you get a linear vector field in the sense of the definition that we gave at the beginning. And then what happens here, and of course the flow associated with A is just the matrix exponential of A, and it's also automorphism of your abelian group here. So it comes as a natural generalization of this kind of system. And for this usual system, the derivation that you get, the classical system, the derivation that you get the matrix A, and you identify, because here the group and algebra can be identified, the exponential here is just the identity, and then what you get here is the identification between group and algebra, this group G plus and G minus and G0. And for this kind of system, we had already some results relating G plus, G minus, and G0 with the dynamical properties of your system. And what we did in this subsequent work, I basically the idea was, can we pass most of the properties that happens in the abelian case for the general case? And the main topological properties that we have that are shared also with the abelian case is that all of these subgroups, they are closed, they have trivial intersection. When you think about generalized eigenspace or some of them, it's exactly what happens. And we have some sort of normalization here in the sense that G plus and G minus, they are invariant by conjugation of G0, that in the abelian case is trivial one. And here you have also some sort of decomposition as manifold of your group in some case. Okay, you can decompose your group as this product here when your group is solvable, or when this component G0 is a compact subgroup. Okay, so, and those are just topological properties of the groups. And what are the relationship between this subgroups and the actual behavior, dynamical behavior of your system? And the point is that when you assume this strong condition here, it's strong, but it's something in between, because in the abelian case, when you ask for this condition, here you have the well-known Kalman condition that basically says that your matrix A evaluated at the columns of your matrix B, but as product, it generated the whole Rn. And if you generalize this kind of condition for Lie groups, we call ad-Hankran condition. This condition is also true. You still have that the E is a point inside of its attainable set. Okay, so we are still looking into this, but the point is, when you have this strong topological condition, there's a natural relationship between these subgroups and your attainable set. And why from the identity, and why this attainable set from the identity it's so important to analyze, because I just think if you want to look, for instance, at controllability property, meaning that you want to connect 2 points of your state space, it's enough to connect 2 points passing by the identity element. So you go in positive time from this given point to the identity, and then from the identity to the second given point, and then you get controllability. So, and in here, that's a star means exactly that, is the attainable set in negative time, or what we call the controllable points, that the points that can be controllable through the identity element of G. And under this topological condition, what you have is that the product of G plus and G0, that's a subgroup, it's inside your attainable set from the identity. And the -1, G minus G0 is defined the same way, is in the set of the controllable points. And this condition also, in fact, it's equivalent to the existence of a control set D that contains E in its interior. So when this control set exists, it actually satisfies the following condition. It contains the whole of G0, okay? And if G is decomposable in the sense that if you can decompose G as the product of these three submanifolds, this control set D is actually the only control set with no empty interior. There's no other one in your whole group with no empty interior. And in particular, you have two other conditions here, that if you do not have eigenvalues with negative real part, and then actually your D is just the controllable set from the identity, is in particular open. And if you do not have eigenvalues with positive real part, and then you have the opposite one, your control set is closed and coincides with the closure of the attainable set. And actually in the nilpotent case, you have also the converse here. So if you have an open control set, and then your group has, in fact, the associated derivation A has no eigenvalues with negative real part, and also the fifth condition also. And all of these conditions also naturally holds for the abelian case. And the one that we wanted to study, and we have some progress in the last years, was when can I say that my control set's bounded? Bounded control sets are interesting because, for instance, I worked with the concept of invariance entropy, and usually you work with bounded subsets in order to achieve more refined results. And for the abelian case, it was enough to assure that your matrix is hyperbolic, in the sense that you don't have eigenvalues on the imaginary x. So, but when you look at linear control system on compact Lie groups, you also have controllability just by the Lie algebra rank condition. Okay, so meaning that in the compact case, if you have that just G0 is the whole group, it's in fact controllable. So how can we look at this, both of this behavior? And what happens in general is that if your component G0 is compact, in fact, your control set is necessarily bounded. The idea here is basically to reduce our system in a semi-direct product of this compact subgroup G0 by what we call G plus minus. That's the product of G plus and G minus, when this product is in fact a subgroup. It cannot be a subgroup because you can have products, or just thinking at the algebra level, you can have products of elements in G plus and G minus that goes to G0, because by the derivation properties, what you have is that the bracket between vectors in different generalized eigenspace goes to the generalized eigenspace that's the sum of these vectors. So you can certainly have directions that you positive direction, negative one, that when you do the bracket, it goes to G0. So, but when you have this compactness of this group, what you can show actually is that this direction, all of G plus minus, all of the elements associated to G plus and to G minus, they are inside the nilpotent radical of your group. And that solves the problem, because the bracket between elements inside the new radical of your group will still remain there. So if G0 is compact, the G0 part inside the G0 radical is in the center, and you can get rid of that. When you get rid, and then your G plus minus the subgroup. And then you get, it's a very technical, but the result is basically that. And then why did I call the structural properties? Is because compactness also gives something more, something that has to do with the whole control set, or actually the closure of the control set. It allows us to define a continuous map that goes from the set of your control functions U inside this subset, this product manifold here, G plus minus. And this map here, it's a well-defined map, and it's defined just by the definition is just it associates an XU here that has bounded orbit. So when you consider the orbit starting in XU in positive and negative time, it is bounded. Okay, there's just one point, and you can in fact associate it to any contour U, this point. And from that, you get a nice relationship between your control set and your set of the contour functions in the following way. Just define the lift of your control set as being the points of the form, like the points in the Cartesian product whose orbits remains inside the closure of your control set. Okay, that's called usually the lift. And what you have is that using this function, this continuous function here, you can define a function from the Cartesian of U times G0 now, your compact, this compact fiber here. And what you get is that this map here is actually a continuous map. It's exactly the lift of your control set. And a very interesting feature here is that when you have that G plus minus is actually a subgroup, and meaning that, of course, it does not happen always, but you can always consider a quotient of your group by a compact subgroup in order to obtain G plus minus as a subgroup. And then there's a natural induced linear system on G0 that's identified with this quotient here. And what you get is that this map H actually conjugate what you call the contour flow in this Cartesian product with the contour flow restrict to the lift. The contour flow is basically the skew product flow that we get when you consider in the first component the shift of your subset U here and the solution of the system on G. Okay, so you get this conjugate, and this kind of conjugations can, at least up the top, what I think is that we could work, for instance, with some properties related to optimality inside your control set. For instance, you can relate with just by looking at properties of this induced system on U times G. Okay, so this semi-conjugation between the system can be used to apply some things. Okay, so that's the most structural property that we had here, and that generalized. I'll give you one example in R2, a really well-known system here. Okay, when you consider this, basically your derivation and your matrix B or your invariant vector field is the constant one. And in this case, it's not hard to see that this matrix here is hyperbolic in the sense that we commented before, has no pure imaginary eigenvalue. And here it's also not hard to see that G plus and G minus, they have this, they are given by this span, and G0 is just the identity. So that's the usual result that was proved in several references. And in this case, it's also well known that the control set is just this Cartesian product of -1 and -1, 1 open in the first component and -1, 1 closed in the second one. Okay, and here you see that the closure of the control set is also bounded. And for this case, and actually that's the whole idea to obtain this point XU. It comes from this idea in the abelian case. You can get the point XU for U periodic functions, okay? And what you get is basically that, some integral here with this weight. And you can associate this point XU. And in the general case is also a little bit similar. You also get some relationship with that and with the, you strongly use the fact that your derivation in this G plus minus has no zero eigenvalue, okay? So, and then like to finish, a second example here is just a control set that is not bounded, okay? When you consider this product here, it's another interpretation of the solvable Lie group, two-dimensional solvable Lie group, and then you have left invariant vector field given by that, with this interpretation here. And what you get is a linear control system has basically this form. Okay? And for this kind of control system, you have in particular that your G0 is just the positive line, the positive X line. And here, your control set is basically, as I said before, the closure of your attainable set from the identity. Here I'm choosing B to be negative. I needed to make this choose because otherwise it would be open, the control set. And you have this like nice property, this nice control set here that's basically a column. So basically what we have with this kind of relationship is that you can get most of the topological properties of your dynamical properties, at least related with controllability, and control sets of a given linear control system with just by looking at the eigenvalues of your derivation associated. Okay, so that's it. Time is short, so thank you very much.
Thank you, Adriano. Questions, comments? Please, Professor Philippe.
Yes, Adriano, can you say more about the function you call X of U, the function that at control U associates the points, the only points where something is, the trajectory is bounded, something like this. Can you come back to that?
Yes, basically, I have this manuscript open. Just 1 second, I can show you. Basically, what we get, you can see this here. Basically, it's this proposition. I don't know if you guys can see the proposition 2.6. Here, basically, what you get is that you needed to work with this this alternative function here that associated to n point of G, this G product with C G minus 1. And using this, and that's exactly the function when here I'm calling hyperbolic in the sense that your group is G plus minus. Okay, you have no eigenvalues in the complex X axis. So that's exactly what happens in this case here. The abelian case, when you have this expression here, this expression is just the calculation of this function that I'm showing to you. And the basic idea is consider this kind of function, and then you apply this function on the solution at time tau. And this tau is related with the period of your control. But before you do that, since you have in the non-abelian case, you have you can decompose this solution in a part that's in G plus minus and G0. You have somehow to make some arrangements with G0. And that's not the case in the abelian case, because G0 is always 0. So basically what you do is apply this kind of function exactly to the solution at time tau. And that gives you the point xu that you have. And the points that are not related to periodic one, you just obtain by limit and uniqueness of the limit.
Okay, thank you.
It's interesting because you have a way to obtain the points, exactly. After some remarks and some decompositions, you have a way to obtain points.
Okay. Okay, thanks, Adriano.
More questions? So, please, Rafael.
Adriano,
Yes.
You can say something about control sets. What not contain the identity, the neutral elements of the group.
So we have some examples. The main part of examples, all that you have is that or the control sets are they have empty interior, or the control sets have no empty interior and satisfy this condition. But all the examples are in low dimensional ones. So for high dimensional case, I really don't know. We are start to thinking about what happens with a control set that has the control set that has the identity element in its boundary. And if this control set has no empty interior, which conditions do we need to have in order that this point goes, the point E is actually inside the interior of your control set? Okay, and the idea is to start working with the case where your G0 is in fact compact subgroup and see if we get something. But in general, I really don't know.
Okay.
So let's thank Professor Adriano again.